Thanks. Begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students and for the visitors, if there are any. Just help us to have a good day today and to glorify you, learn what we do. In your name I pray, Lord Jesus. Amen. All right. I feel like there's a visitor here. Aha! Are you interested in the math major?
Yeah, I am. I'm either going to do math major or I'm going to be a math teacher. I have to decide.
Okay. Very good. Yeah, this is one of those courses you'll have to take. It's probably a little bit detached from things you've seen in high school. I mean, we mostly do proofs in here. It's not like math you typically see before you get to university. But anyway, so this is, today we're talking about linear independence. And spanning in the abstract context. So last time, right, in vector spaces. So what, you're like, well, didn't we already talk about linear independence and spanning? Well, yeah, we did, but what did we do that for? We did it really, for the most part, for column vectors, right? So today I want to extend that discussion now to abstract vector spaces. But before we do that, I still have a few sort of examples left over from our last discussion. So, but first, a few subspace examples, all right? So example 1, we should think about the vector space F of, say, functions from the reals to the reals. So in other words, this is the vector space of functions that go from the reals to the reals, right? This forms a vector space because the sum of such functions is, again, such a function. The scalar multiple of a real valued function of real variable is a real valued function of real variable. And the addition of functions satisfies those 10 axioms, as does the scalar multiplication, right? Technically, this is a special case of that sort of meta example I gave last time, right? In this case, the W, the target vector space, W is equal to the reals. The reals is a vector space. And so vector space, this is a typical, so here F is a vector in this context, all right? And what's the, what base field are we going to use? What field? This is over what? My choice of my F is going to be the reals, all right? So that's the universe for example 1. Now let's think about some subspaces. What kind of special function types do you know? Oh, how about polynomials? Polynomial functions. So you could say R of x, right? So what this would be f of x such that f of x is equal to an x to the n plus a1x plus a naught, for some a0 through an in the reals. In other words, this is the set of polynomials, right? We could look at this as a set of functions. Would this pass the subspace test? I'm going to write it out in words. Since f of x and g of x in the polynomials over x implies f of x plus g of x, and c times f of x, again, in R of x, right? We have the set of polynomials. So I'm thinking of this as the W from last class, all right? W is a subset of V. It's closed under addition. It's closed under scalar multiplication. What else do I need to apply the subspace test? One other thing, right? I need it's non-empty, right? So could you show me that the set of polynomials is non-empty? In other words, do you know any polynomial function that you could tell me? 1? Okay, yeah, sure. F of x equals to 1 is a polynomial function. So that's an element of W, which is then not equal to the empty set, right? Therefore, by the subspace test, W is a subset of V. Now, I would give you partial credit for my current solution if this was a test question, right? What's missing? I didn't really show you the details of why this or that is true, did I? Let me expand on that over here. So if f of x and g of x are polynomials, right? That means that f of x is something like, you know, oh, well, an x to the n a2x squared plus a1x plus a naught, right? And g of x is something like b sub m, x to the m, b2, x squared plus b1x plus b naught, right? There's a lazier notation we could use for this, right? How about this? Why don't we instead say that this is the sum n equals 0 to infinity of a sub m x to the m, oh, n. And I shouldn't use that. Let me say, sorry, different letter, j, a sub j. J equals 0 to infinity of a sub j x to the j. And this we might as well say this is the sum j equals 0 to infinity of b sub j x to the j. You're like, but you haven't told me any notion of convergence here, right? Like in Calculus 2, we spent a long time talking about how convergence needs to be carefully dealt with. Because if you're not careful, you get into contradictions, right? So this is just, this notation is just a sneaky way of saying it goes on and on. Well, it doesn't have to go on forever, but here, these are both with what? With a sub j, b sub j, not equal to 0 for finitely many, right? Many j. That's another way you could describe a polynomial, right? It's an infinite series where you only have finitely many non-zero terms. That's actually a very convenient thing, because otherwise I have to fiddle around with which is larger, m or n, right? And then I have to extend the ones so they can match up and actually add them. It's kind of it's a notational quagmire. So if I use that notation, it's a little bit easier, because then I look at f of x plus g of x, what do I got? Sum j equals 1 to infinity. When I add them, and really I'm just giving you the definition of how we add polynomials. Well, fine, that's not, I've introduced them as functions here, so I suppose you could.
You want to get started on?
Oh, no, those are both zeros, so sorry. But anyway, here we go. So that's the sum j equals 0 to infinity of a sub j plus b sub j. How do I know that that is a polynomial? Well, if a sub j and b sub j are finite only for finitely many j, it's still the case that a sub j plus b sub j is non-zero for finitely many j. So it's still a polynomial. In other words, this is the sum of two polynomials is a polynomial. Now, do you have to use the sum j equals 0 to infinity notation? Not really, right? You could use the plus dot dot notation I started with. But there you should say something about the fact that if you add different degrees, you can't assume they both have the same degree when you add them. So that you have to address that in your argument. And let's see here, while we're at it, we could just take c here, like that, right? That puts a c here, which puts a c here, right? And again, that's a polynomial. So this shows that c f of x plus g of x is a polynomial, right? And actually, this exposes, I mean, I had 2 steps for the subspace test last time, right? But computationally, we can combine both of these steps into one step, if you think about it, right? If I can show that whenever f and g are in the polynomials, it implies that, c, f plus g is in the polynomials. If you look at that, special cases of that give us both of the things we need, right? Like on the one hand, if we put c equals to 1, we get f of x plus g of x, right? And if we put g equals to 0, we get the other thing, right? And these are the 2 ingredients we need: closure under addition and closure under scalar multiplication. Those are the things I need, paired with the fact that W is non-zero subset of V to show it's a subspace. Right. Sorry, I thought I should actually put some details in here, in that I just took points away from you guys for not putting these kinds of picky details. So, to be fair, here's some picky details. All right, let's be slightly less picky in what follows. What other subspaces of V can you think of? How about this? How about this W2? We could do, how about this, C0R? In other words, this is the set of continuous functions. Is the sum of continuous functions a continuous function? This is one of the things we learn in Calculus 1. Yeah, the sum of continuous functions is continuous functions. How about if we take the sum of once differentiable functions, or once continuously differentiable functions? You could look at these so in other words, f prime exists and is continuous, the space of once continuously differentiable functions. Is the sum of such things, again, such a thing? In other words, if I can differentiate f and I can differentiate g, can I differentiate f plus g? Yes, the derivative is the sum of the derivatives. And if both f prime and g prime are continuous, then f prime plus g prime is continuous. Can I scalar multiply a differentiable function and get another differentiable function? Yeah. Right? These all basically follow from the fact that we have this rule for derivatives, right? So that rule of differentiation implies that the sum of differentiable functions is differentiable and scalar multiple. And hence, W3 forms a subspace of V. Can you guys think of any other subspaces of functions? Here's some boring ones: twice differentiable, thrice differentiable, 4 times differentiable. You could talk about smooth functions. What's a smooth function? That means you can take as many derivatives as you like, and they're all continuous, right? Sum of smooth functions is smooth. The scalar multiple of a smooth function is smooth. Another subspace. Calculus 2, you learned about power series, right? You learned about functions which are entire, like sine, cosine, exponential. These have power series which converge for all real numbers. If you take the sum of 2 such functions, 2 functions which are representable by power series on the whole real line, the sum of those is again entire. So entire functions forms a subspace. Things with power series. You can also call them analytic on R. So there's all kinds of interesting subspaces of function space. Here's another one. You could look at, how about this? W prime 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 equals to 0 has solution set W. All right, I'm claiming that the solution set W is in fact a subspace of V. This differential equation has a subspace, which is has a solution set which is a subspace. How do you solve this differential equation? I'll get us started. Y prime prime ddx of that is equal to 0. So that tells me that y prime prime is equal to a constant, c1, right? If the derivative is 0, it must be a constant. Having done this once, I can't resist but do it again. So d dx of y prime equals to c1. So integrate both sides. This gives me y prime is c1x plus c2. So that's dy dx, of course. Integrate again, I get y is equal to 1/2 c1, 1/2 c1x squared plus c2x plus c3. Actually, I didn't need to do that to prove that this was a subspace. So sorry. How should I prove that the solution set is a subspace? Save, don't erase this. This will be useful for us in a bit. But to show it's a solution set as a subspace, what I really need to do is to let y1 and y2 be in W, right? And let's let C be a real number. Consider what? How about consider cy1 plus y2 prime 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 equals to what? What are the rules for triple differentiation? Is it the triple derivative of the sum of the triple derivatives? And can you pull scalar multiples out of triple derivatives? Indubitably. It is in fact possible, yes. At least that's the sort of thing we learn in the residential calculus here. So now, well, I don't know, maybe you don't. Maybe Dr. Sprano gets fed up after 2. I don't know. But seems like he probably teaches triple derivatives. That's 0. That's 0 by assumption that W1 and W2, I mean, Y1 and Y2 are in W, right? So what does that show? The third derivative of cy1 plus y2 is 0, which shows us what? Therefore, cy1 plus y2 is in W again. So what's that tell me? Hence, cy1 and y1 plus y2 are in W. And since, so you guys, I just need one 3 times differentiable function. I need to show W is non-empty, right? This is not hard work, but it's work we need to do. Can you guys give me one function which is 3 times differentiable? What's that? X cubed. All right, that's exciting. Why not? Well, it also needs to be in here. So x cubed actually won't work because, I mean, I set you up for the fall because I asked you for just 3 times differentiable, but I need more than that, right? I need it to have the third derivative being 0 to be in W. X squared, yeah, okay. So if we look at x squared, y equals x squared has y prime 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 equal to 0. Therefore, x squared is an element of W, which is non-empty. Thus, W is again a subspace of the function space from the reals to the reals by the subspace test. All right. Okay, so I think I've done enough of those at this point. A few more examples, though. This time we're going to let V be our 2 by 2. All right. And actually, you know what? We're going to let it be C2 by 2 to be more interesting. C2 by 2. Complex 2 by 2 matrices. Let's look at W, which is A in C2 by 2, such that, you know, A11 plus A22 equals to 2. I'll call that W1. W2, I'm going to say complex 2 by 2 matrix such that, let's see here, how about I times A plus 3 times A is equal to 0. That's not going to work. That's not what I want. I'm sorry. Oh, I'm sorry. I'm just can't think of a good example at the moment. How about that one, though? Let's just talk about that one. Can you guys tell me why W1 is not a subspace of V? I'll let you think about that. I'm going to throw another one up here on the board while you're thinking about it. We could look at V to be R2 over the reals. Or, yeah, over the reals. And I could let W say equal to x comma y such that x and y are greater than or equal to 0. So for my example 2, tell me why that's not a subspace. What do we need for it? It has to be a vector space with respect to the operations of, complex 2 by 2 matrices. Why is that not? Nobody? Well, so you have not started working on your homework then, I can tell. Because the first problem is just this. There's like 5 of these. Yep. Ah, very nice. So if we looked at A equal to A11, A12, A21, A22, you're like, if you scalar multiply that, you get CA11, CA12, CA21, and CA22. So if A11 plus A22 equals to 2, then CA11 plus CA22 would equal to 2C, which would probably not be equal to 2 if C was not equal to 1. Which then implies that if A is in W, it does not imply that CA is in W. That is definitely a trouble. Yeah. So, I mean, if you're going to give a counterexample, set C equals to 2, pick a specific matrix, If you want to disprove something, give me a specific matrix and show me that it fails, Like, for example, what do we got? The identity matrix is in here, right? But 2i is not an element of W. So this is all W not subspace, since I is in W, but 2i is not in W, right? Because I11 plus I22 is equal to 1 plus 1, which is 2, but in 2i, we have 2i11 is 2, and 2i22 is 2, and 2 plus 2 is 4, which is not equal to 2. Very good. Can anybody think of another thing? I'll tell you. This example 2, additive inverses doesn't work, right? Additive inverses are not in there. If I look at A, if I look at minus A is going to have A11, it's going to have minus A11 plus minus A22 to be equal to minus 2. 0 is not in there. 0 is not in W1. How about this one? 0 is in here, right? But we have you can kind of picture what's wrong here. We have all of this up here, right? So you pick any vector in there, pretty much any one, right? Minus it is over here. And that's not present in the set, so it's not a subspace. All right, well, enough of that. You have some homework that should help you round out that idea. So I'll leave it to there. So let's talk about linear independence and spanning. So definition, we have S is a subset of V, a vector space, and let's say v over f, okay, is linearly independent if c1, s1 plus plus ck sk equals to 0 implies that c1 equal to 0, c2 equal to 0. Well, I guess I'm just writing 1, okay. c1 all the way out to ck equals to 0 for any, selection of s1 through k in S. So this definition allows for the possibility that S is an infinite set. So if we have an infinite set, linear independence is judged by any finite linear combination of them being set to 0, implies that all of the coefficients are 0. In the case that S is a finite set, we can just say, take a linear combination of everything in S, right? That equal to 0 should imply all the coefficients are 0. It's just that I've stated it in a slightly slippery way to allow for the case that S could be infinite, right? Even if S is infinite, though, we look at finite linear combinations set to 0. The point is, any one of those has to imply that all the coefficients are 0 for linear independence. See, V could be an infinite set. Well, V usually is. That's the one definition. The other definition is that the span of S is likewise the set of all finite linear combinations taken from S. So it's going to be the sum, let's see here, j equals 1 to k of c sub j, s sub j, such that cj is in F, k is a natural number, and the s sub j's are in S. I forgot to say something up in the previous one, which was what? Kind of important. It's for any S1 through SK, and, well, I mean, I don't know where to write it exactly. I mean, I probably should put it up here for usual grammatical reasons. For C1, C2, CK, where? Taken from where? These are scalars taken from the field of consideration, okay? But this is precisely the notion of linear independence and span we had before, right? So let's look at here I'll show you an infinite example. Example 4, I suppose. Let's consider the set S as 1, x squared, without end, okay? So the set of all monomials in X. My claim is that this is a linearly independent subset of the polynomials in X. So did I use that notation already today? I think I did. So the polynomials in X. Right. So if we take any, so we should just look at a linear combination, right? So the proof, it looks like this. Consider C1 plus C2x plus plus, let's say Cnx to the n equals to 0, right? I guess I should use k there to be consistent with my definition. Do you want me to put k there? I'm going to leave it as n, though, because it'll make the next step more friendly to you guys. So let's, suppose we have that. My goal is then to show what? All of the coefficients need to be 0. Of course, if you've studied calculus, you already know that that's an inevitable fact, right? If a polynomial is set equal to 0 for all x, it must mean that the coefficients are separately 0. You use this all the time. If I tell you ax squared plus bx plus c is equal to 7x squared minus 2x plus 3, you can tell me what a, b, and c are without flinching, right? A is 7, b is minus 2, c is 3. What you're actually using there is the fact that a minus 7 x squared plus b plus 2x plus c minus 3 equals to 0 must be the 0 polynomial. That implies the coefficients are all separately vanishing. In particular, that a minus 7 is 0, that b plus 2 is 0, that c minus 3 is 0 separately. The reason I can do that is because 1, x, and x squared are linearly independent. See, linear independence also implies that you can equate coefficients. That's one of my next theorems. All right, but let's prove it. So first step, how about this? This has to be true for all x in the reals, okay? It's actually a function equation, right? So what's our favorite x then for that equation? 1, pi, e, natural log of 2. Probably not none of the above, right? How about 0? Yeah, okay, yeah. Set x equal to 0, what do we get? C1 equal to 0. Well, there's 1 down and minus 1 to go, right? So what's your next move? Well, this is a polynomial function over the reals. It's true for all x. That means we can differentiate this equation star, right? So the derivative with respect to x of that star equation gives me what? It gives me c2 plus 2c3x, not written, plus n cn x to the n minus 1 equal to 0, right? For lack of imagination, let me call this equation star star, also known as star squared. Evaluate star squared at x equal to 0. What do we get? C2 equal to 0. X equal to 0 in star squared. Obtain C2 equals to 0. Now we continue in this fashion, right? Until we get what? How many times do we do this before we get down to just the last coefficient? How many different derivatives do I have to take? N. And so that would be what? N minus 1, 3 times 2 times 1, Cn equal to 0. Which, of course, then implies that Cn equal to 0. So we get all the coefficients are 0. Now, if this is not careful enough for you, you should feel in your bones that you could do an induction here and make it more careful, right? But I'm not going to take class time to do that. Going forward, the more important point to know here is that we now have that S1, that the set of monomials in X is a linearly independent set. Yay. All right. By the way, is a subset of a linearly independent set linearly independent? Oh, I shouldn't erase that. If I took a subset of a linearly independent set, could I get linear independence of a subset? Do you know what I mean? Suppose T is a subset of S, and this is linearly independent over F in some vector space, right? Think about it. If you take C1 T1 plus plus CK TK equals to 0 for some, T1 T2 TK in T, and, coefficients C1 in the field, then what? It's very dumb. Why does this imply? This implies C1 equals to 0 all the way down the line, CK equals to 0, why?
Because if we just consider the fact that even removing 1 plus
Okay.
It doesn't have to be a proper
Get
subset.
in there. Get in there.
But even removing one element, no combination of them will equal.
Too complicated. Too complicated. What do we know about the t's? T is a subset of S, right? What you were saying is, I think, intuitively true, but like we can. All you need to say is that since T is a subset of S, right? What's that mean? That means that the T1 through Tk are actually where? These are in S, right? So by the definition of linear independence, if I have a linear combination of them equal to 0, they're from a linearly independent set, that immediately implies that these are 0. I think what you're about to tell me was if I had a linear dependence in T, that would imply there was a linear dependence in S, which is a contradiction. Is that right?
You've lost me.
Well, you're starting to talk about writing one in terms of the other, right? Yeah. So if you could write one in terms of the other inside T, that would imply that you could write one in terms of the others inside S, which would then contradict the linear independence of S. I'm sorry. I was trying to be, clairvoyance is not one of my gifts. And I cut you off mid-sentence, so it's all my fault. Anyway, sorry about that. It's all my fault. But since this. So anyway, yes, any subset of a linearly independent set is linearly independent. Was the empty set linearly independent? I think by default, right? If you take any linear combination of vectors in the empty set, it implies the coefficients are 0. Well, you can't violate that because there's no vectors to take linear combinations of. So by default, yeah, the empty set, which is good because if it wasn't linearly independent, it would be troubling when I said any subset of a linearly independent set is linearly independent, right? The empty set's a subset of any set. So that'd be annoying if it was not. Then I have to make a side comment here. Anyway, my larger point is if you take any selection of these, right? If I take just the even powers, that's also linearly independent because that's a subset. Or if I just take the odd powers, linearly independent. Any selection of monomials, linearly independent in the set of polynomials. All right. So, span. So, if this set S is also called a generating set. If I take this whole thing and call it W, all right, then S is generating set, or sometimes called a spanning set. Generating set for W. So we could go back over to my triple derivative being 0 calculation, and we could find a spanning set for the solution set over there, right? We already did all the work. See this right here? This shows you that any solution, y, in the solution set is in the span of what set? I can build everything in the solution set from taking a linear combination of 1/2 x squared, x, and 1. That's immediate from what's right above here. Every solution to the triple derivative equal to 0 is a linear combination of 1/2 x squared, x, and it's hard to see, but that's c3 times 1. So this guy is a generating set, or a spanning set, for the solution set to this differential equation. Furthermore, it's not hard to see that I could erase the half, right? Do you guys see I could erase the half? And I could erase that half. All I would have to do is do, it's still the case. C1 over 2 is just an arbitrary constant. So I could still get everything here from linear combinations of these three. And by my previous example, this is in fact a linearly independent set. So in fact, here we have x squared, x comma 1 is linearly independent spanning set for W. The whole next class we're talking about this. If a set is both linearly independent and a spanning set for a subspace, then it's called a basis. So this gives us a linearly independent spanning set is called a basis. Put both of them together, you get basis. By the way, we will prove in due time that the number of vectors in a basis, if it's finite, must be the same for any choice of basis. All right? And the number of vectors in the basis is called the dimension of the space. All right? So what we will learn soon is that because there are three things in this basis, this makes the solution set three-dimensional over the reals. So the dimension of a vector space is the number of elements in the basis. I can't make those definitions yet because we haven't earned the right to say that the number of things in the basis is an invariant of the vector space. It'll take me an hour of work to prove that. All right, so let's continue down the path. What else can you say about spans? Well, there's some kind of really sort of interesting things you can say about spans. Here's one of those. The linear combination of linear combinations is a linear combination. No, I'm actually saying something. Yeah, I know. So here's it's fine. Here's the proof. Let's consider S sub I equal to the sum, all right, j equals 1 to n sub I, all right, Cij, Tij. So this is a bunch of linear combinations. I have, as my I ranges, I get a linear combination for each I. All right? So for Cij in the field and Tij taken from some set S, which is a subset of some vector space over field. So then if you consider the sum over B sub I, S sub I, that would be I equals 1 to however many of those I got. I said I got k of them. Here I equals 1 to k. So I've got k linear combinations of possibly different lengths. Each has length n sub I. N sub 1, n sub 2, n sub 3, n sub k, different linear combinations. Take a linear combination of those. That would be this. Well, that's just and the thing is, by the rules of finite sums, I can pull the scalars out, rearrange it into just a sum. I equals 1 to k. Sum j equals 1 to n sub I of B sub I, C sub ij, Tij. This is, again, an element of the field, and the Tij's are vectors. That's a linear combination. So yes, a linear combination of linear combinations is a linear combination. Why do we care? Besides just word soup. Why do we care? Because we get the following theorem. Theorem. If V is vector space over F, and if S is a subset of V, right, then span of S is a subspace of V. I really feel like this really deserves more than I think this deserves an exclamation point, because that's pretty awesome. I mean, that means that if you can recognize your set as a span, that proves it is a subspace. How do we prove that? We prove it by the subspace test theorem. How would you prove? So what would you take two things in the span, right? Take two elements of the span. What are they? They're both linear combinations, right? That's what the span is. It's the set of all linear combinations. Is the sum of linear combinations a linear combination? Indeed it is. Scalar multiplication, scalar multiple of a linear combination, is that a linear combination? In fact, it is. Is there anything in span S? Is it non-empty? Yes. In fact, S is a subset of span S, right? Pick any vector in S, right? Multiply it. 0 is always in span S, right? Even if it's the empty set, the span of the empty set is defined to be 0. If there's a vector in S, 0 times that vector gives you the 0 vector. So 0 is always in the span of S, which is non-empty. So it's non-empty and it passes a subspace test. Therefore, span S is a subspace. This is wonderful. Check it out. Example. And this, this is a gift I try to give on the next test, and so many of you refuse to receive this gift. This is a gift I try to give, but it is so often not taken. So something like this. A plus B, C minus D, A plus 3B, such that A, B, C, D. I don't want a D here. Let me just put a C. There, C. A, B, C. In the reals, is this a subspace of R3? So here I'll express that as subspace question mark R3. Let me make it more exciting. Let me make this middle C be A. There we go. The point is, this we can rewrite as A times 1, 1, 1 plus B times 1, 0, 3, such that A and B, there was no C. A and B are real numbers. But what is that? That is a linear combination. That is, in fact, the span of what and what? In fact, it's the span of 111 and 103. So is it a subspace? Yes, it is. I just wrote it as a span. Game over. That's it. In fact, I can tell you that the dimension of W is 2, because this, in fact, forms a basis for W, because 111 and 103 are linearly independent. So those two vectors give us a natural basis for W as well. All right, so I have a smattering of theorems about linear independence I still need to say in here next time, right? And there's some examples I've missed here and there. I hope you read. Like, I've not talked in class yet about the Cartesian product of vector spaces being a vector space. I still need to introduce row space, column space, null space, but all in good time. I'll try to weave those into the discussion going forward of basis. So have a good weekend, guys. And if you haven't already gotten your homework, mission 3.